Okay, sorry, is this working? I'd like to start off by the usual thanking the organisers, though I must say I'd like to add a little bit of a superlative to that, because this does seem to be a particularly amazing conference and a particularly well organised and obviously well funded operation here. Thanks to the Isaac Newton for putting this on. It works. Okay, so I'm talking about the meataxe. I guess probably most of you got some idea what that's all about. Put the early history in here. John Thackeray and I started working on this with matrices in 1977, I think, or 78 maybe. And until 1995, computers just got bigger, better, faster, and the basic techniques that you needed to program them basically changed very little. So Steve Linton once said that every program you can solve NP complete in polynomial time. You just wait the correct number of years until computers get more powerful, faster, and then your program will run in no time at all, in 0, nichts. So basically what you had to do, well, let's see if I can operate this. Okay, speed depended on doing as little work as possible to achieve the result you wanted. And that's basically what programming was like until 1995. And then in 1995, basically the hardware development changed direction. The limits of physics came along and rather irritatingly stuck you at about a gigahertz of clock speed and so on. So it got in the way of further development. So Linton's algorithm no longer converted an NP complete problem into a polynomial time one. And so you had to figure out how to do more things at once. And that's what the chip designers did, Intel, AMD and so on in particular. Everyone just ignored this and hoped it would go away. And I don't think it's too inappropriate to say that they continue to do so. And so my talk here is a rant, really. So quite a lot of you have heard this before, of course, but I'm going to rant again anyway. So our work on the meataxe basically split, and Ringer and Lux and Thackeray continued to develop stuff to make it more user-friendly. The idea is that you want to be able to actually use this stuff, which is a perfectly laudable objective. I've got no problem with that. But I was just obsessed with performance. I never put it down. I want to be able to multiply and do Gaussian elimination and all the things that we did in 1977, which were not very many, basically split and tensor product and add and multiply, and that's about it. Ease of use was not on my radar. So anyone who's tried to use my programs will know perfectly well how high ease of use is on my priority list. It's down there somewhere. And at some point we are going to need to find a way of reuniting the parts. I'm really up for that, but haven't started yet really. Anyway, well, it started a bit. From 2015 onwards, all sorts of new technology came along. People have come up with these graphics accelerators and artificial intelligence accelerators and so on. They haven't stabilized. If you're going to work on a project that you're hoping will run for 20 years or something, you can't afford to run your stuff in CUDA. Will NVIDIA CUDA stuff still be running in 20 years' time? Well, I don't think so. I mean, there might be. I might be wrong. But I guess that moving data about is harder than doing the work. This is what I found with these GPU chips. It's all very well that they can multiply floating point numbers at an unbelievable lick, but you've got to give them some floating point numbers to multiply, and that is actually a bigger problem. I don't know. I feel it's a general observation, but we'll see. So I don't know. I use the word x86. I don't know how many people know what an x86 is. They probably do, but to bore everybody that does, every computer probably that is in this room is an x86. Every computer in almost every server room is an x86. It's anything that's produced by Intel or AMD, basically. But it's not an ARM. I'm not talking about stuff in your phone. So if you want to use your phone to multiply million by million matrices, I would say you're off your head. Having said that, I worry that somebody's done well, and yeah, it's going to happen, obviously. But I'm concentrating on the x86. So what's happened with the x86 is that it's stabilized. It is no longer changing like mad. Like when I was first programming in 1977 commercially, I knew that the machine I was programming was going to be totally obsolete in 2 years' time. It's a complete waste of time developing 8 years of software for a computer that's going to be obsolete a quarter of the way through the project. That's no good at all. But now it's stabilized. And again, I'm not sure how obvious it is to people that the computers of today and the computers of 10 years ago are basically the same. They are it's no longer a moving target you're trying to hit. So instruction set's pretty much the same. Not exactly the same. Cache size is pretty much the same. Shared memory architecture, pretty much the same. Vector sizes. They're not changing much. The last 5 years, they've really not changed at all. And, yeah, well, predictions are always dangerous, but I would say they're probably not going to change much in the next 5 years either. So the x86 changes have basically stopped. Tomorrow's computer will look like today's computer. Now, if you look at where they've stopped, you might say the world has gone mad, mate. It is not a sensible place. You've got an amazingly complex and messy set of vector instructions, and in particular, it's not a sensible place, but they've stopped. So you might as well look at what we've got. The computers we're stuck with now are probably the computers we're going to be stuck with for quite a long time. So maybe it's worth looking in considerable detail at where we have stopped and how to use them. Now, this is my rant, of course. So, I mean, most talks at in this week anyway are all about people coming up with magnificent algorithms to do all sorts of wonderful stuff. And if you come up with a better algorithm, of course, you can make it go much better. And all of this is true. That is what most sensible people would do. And it will run typically about 5 times faster, maybe 10 times faster than it would on a computer that you could have bought in 1995. Okay, you get more memory, you get more disk space, but you don't really get that much more power. A better algorithm speed things up by an unbounded amount. Of course they can. You can turn years into 0, nichts by doing things in a better way. Of course you can. Or you can work, sweat and toil your way through implementing the same old algorithm for years and years and make it run 5,000 times faster than it did in 1995. It's really worth the effort. Now, I am speaking from a man who knows. So if you think I'm bonkers, well, you're not alone, right? No sane person would spend 8 years of their life speeding the meataxe up by a factor of 500. I do know that, really. Let me just put my hands up and accept. I do know that. But I feel it's a good idea to see what we can actually do with the computers we actually have. Now, I don't think that's quite as insane as spending 8 years. So I feel I can see a glimpse of the future. I can get some idea. If computers have stopped moving, That's what we're going to have in 5 years' time. That's what we're going to have in 10 years' time. However stupid that may be, let's have a look at it and see what we've got to do to program to use that. So I want to give you a glimpse of what hardware is really like and how you might set about programming it. I'm sorry, you're not going to like it. I do know that. It's not fun. It really isn't. So here's my starting point. So I've been sort of gradually, I guess it was Cooperman and Havas who first noticed the problem with coset enumeration, that you start to hit the memory wall, and that actually having loads and loads of cores doesn't actually help you with your coset enumeration very much. But like everyone else, I ignored it like mad. So I don't want to understand that. That's too hard. But then Max Neunhofer and I sat down in late 2011 and tried to work out how quickly you could actually multiply matrices if you just did it as fast as you possibly can. Start at the bottom, think, how quickly can we exclusive OR stuff? And then Jürgen Müller and I at Nikolaus in 2011 started to say, well, can we actually do that? Can we make it run as fast as that? We could find no reason to believe a 100-fold speed improvement. I'm not talking about speed improvement over a rubbish old program that someone else had written. Right? It's easy to write a paper which says, I've taken this stupid old program and written it properly. I mean, we're talking here about, well, the stuff I'd written, stuff Thackeray had written, the stuff Ringer and Klaus had written. I thought these were pretty good. And I'm looking at a 100-fold speed improvement. Ooh. So here's the estimates we did. This is Neunhofer, me and Jürgen. You've got 12 cores doing 228-bit exclusive OR instructions per clock cycle. You've got 2.5 billion clock cycles per second, and you can use a grease level 4. If you don't know what that means, that's fine. You end up saying, well, we ought to be able to do 30,000 elementary operations per nanosecond. 30,000 operations per nanosecond. That's what that comes to, right? You just work it out. You might need a calculator, but that's what it comes to. So we should be able to multiply 2 square random 470,000 dimensional matrices mod 2 on the Institute of Experimental Mathematics machine, 12 core, in an hour. And so I boasted to Max Neunhofer that that's what I was going to do. Well, it was a bit less ambitious. I said 350,000 in an hour was my target. But I mean, I just looked absolutely ludicrously, amazingly, stupidly fast. So I went to Essen while Jürgen was in charge there, and I worked with Rainer Stachewski. I'm sure I've misspelled that. I probably should have looked it up on Google, but I didn't. And it took 80 minutes rather than 60. I was pretty pleased with that, to be fair. I mean, we learned a lot of mistakes both before and after that. So I'd like to teach you some of these mistakes. Not because I want you to do them, I want you to not do them. So, the talk. What time do I finish, John? I've forgotten. 5:02, thank you. So there's some issues related to matrix multiplication. There's some issues which are really general problems with computers. I'll be going through them in that order, and I'll take a little bit of a commercial break at the end to see what meataxe 64 can do today. So the first thing is you need to allow for local sparsity. So Beth and I, in 2006, I think it was, came up with this magnificent system for multiplying mod 7. And we implemented it, and it was slower than the system we already had, slower than the C meataxe. Why was that? It's because the old system was better with the zeros. So what happens when you've got a matrix that's come out of the meataxe, or some users put it in or whatever, it always seems to have great swathes of zeros. If you've got a system that doesn't deal quickly with those zeros, you are going to lose hand over fist compared to one that does the zeros correctly. So that was not good enough, so that went in the bin. You need to allow for format changes. So if you're trying to multiply matrices, you really need to be able to move matrices from one bit of your system to another. So you need some sort of coherent, constant, uniform format so that what comes out of this can go into that. But that's not what you want for matrix multiplication. If you want to multiply matrices at one hell of a lick, you want to change the format. And in fact, you want 3 different formats. In general, you want an A format for matrix A, so it's the thing on the left. A completely different format, which I call B format, for obvious reasons, for the thing on the right. And what comes out is C format, which may bear little resemblance to what you want either. So you're sort of saying, well, I've got a cubic, typically, multiplication. I want to do quadratic stuff to both the inputs, and then do the cubic as fast as I possibly can, and then do some more quadratic stuff on what comes out. And that's a trick that helped a lot. So what are those formats? I mean, the first thing is it depends on the field. So mod 2, you're going to use exclusive OR. Mod 3, you're probably going to use bit slice, and there's some add subtract codes and floating point stuff and all sorts of things, depending on what the characteristic is. There is no format that you can dream up that will be good for all of them. So you've got all these conversions to do. So it needs to handle such things as sparsity. You've got to look for the zeros in quadratic time. It's no good looking for them when you're going to multiply them. That's in the cubic bit. Get it out. Put your sparsity detection, your grease coding. If you don't know what that is, that's fine. Your padding, so that you can just say, well, I know I've got 1,024 columns. Pow, pow, pow. I'm going to test to see how many columns I've got. If it's less than 1,024, put in some zeros so that it is 1,024. And then the bit slice or float format conversions, they all go in there. And then C format has got all of that. And it also typically completes the reduction mod P. So if you're holding numbers mod 31 in a byte, you don't want to have to reduce them so that they're in the range 0 to 30. It's perfectly good to make sure they don't overflow. As long as they're right mod 31, that's good. So, but when you want the answer, you probably want it in the range 0 to 30, mod 31. So you complete the reduction as it comes out, again, quadratically. The extension fields. So you might think you've got to implement the low-level stuff for every field under the sun. Well, you haven't quite got to do that. What you can do is there's a trick which Martin Olbrecht taught me to convert each extension field matrix into a collection of prime field matrices and multiply them pairwise, and then at the end collect together the answer from that collection of products mod P. So here's an example. I mean, it's actually just caret 2 with this example. So if you've got a matrix over the field of order 4, so every entry is the form R plus Sx, where x satisfies the only polynomial you can use for GF4, x squared plus x plus 1 equals 0. So you make 3 matrices. R is the matrix coming out with the R coordinates. S is the matrix with the S coordinates, and you make T also, which is just R plus S. You do that for both A and B. And then you can compute the R as the product of 2 R's, the S as the product, similarly, of the 2 S's, and T as the product of the 2 T's. And then you can make the answer by computing these 2 things, and then you put it all back together as a GF4 thing at the end. Notice that everything except the multiplication mod P is quadratic. So as the matrices grow bigger, it becomes essentially negligible. So where does that idea go? You need to be able to extract the coefficients from extension field matrix. You've got to be able to do linear operations on the ground field matrices. You've got to be able to multiply them, which is the hard bit, and then reassemble the answer at the end. That's basically what you do with extension fields. So what this means is that you only need high performance multiplication for prime fields. That simplifies the problem quite a bit. So now, how do we multiply matrices mod P? Well, I think you probably have got a fair idea of how to do it mod 2. You just do exclusive OR and that's it. Mod 3, there's a sequence of 6 logical operations. That's 4 exclusive ORs and 2 ANDs, which will add 2 numbers mod 3 coded into 2 separate bits. And there's a coding such that you can do that, such that swapping the 2 bits negates the entries. That saves a factor of 2 on cache. And booth speed encoding, not quite so cache efficient, but very similar. If anyone wants details on all this, of course, all you've got to do is ask me and I will tell you the ad nauseam until you pray for me to go away. Mod 5 and 7, there's vaguely similar sequence that will do this. You can add in 13 steps mod 5 in a way starting with 4 bits for your B format, such that you can multiply by 2, 4 and 3 mod 5 by cycling them. So that again saves a lot of cache space. And there's a similar scheme using 15 logical operations. These are again just adds and exclusive ORs, which all the engineers will know as an half adder and full adder sort of approach. I haven't implemented either of these, I should point out. Again, the details are available on request. I don't know if that 13 is the world record. I suspect it probably is, but if someone's got a better one, then I would like to know. Another trick in this matrix world is the add-subtract codes. Now, this is a more general setting than Greece codes, but the key idea here is that you can't afford to do a data-dependent branch on a modern machine. So this is one of the things I didn't say about modern machines. You can execute typically 4 instructions per clock cycle on a modern Intel. AMD claim they can do 6. But if you do a branch, it has to guess where your program's going to go. And typically that branch will be predicted and it will shove instructions and hundreds of instructions into the pool. And if it guesses wrong, it goes bang on the red button. The whole thing has to be thrown away and start again. And typically 20 clock cycles go west, which is time for doing 80 instructions, which with vectorization could easily be, should we say, 300 or 400 additions. So you really can't afford to have data-dependent branches. So the great thing about the AS codes is that I'm going to take this row and I'm going to subtract that row, and nothing depends on the data. The only thing that depends on the data is which row I'm going to add and which row I'm going to subtract. So you can do that without a data-dependent branch. So here's a little exercise for the reader. I claim that is an AS code. So I claim that every number mod 41 is one of these guys minus another one. Now this is so easy to pick up. So I'm saying that every number is the difference of 2 of these mod 41. So 0 is 0 minus 0, and 1 minus 0, 2 minus 0, 3 minus 0, 4 minus 0 will give you the next. Might take you a few seconds to find 5, which is 15 minus 10. But 6 isn't so hard. That's 10 minus 4, and 7 is 10 minus 3, and then you go up to 15 and 20. And then the other observation is that you haven't got to go any further than 20, because if you want minus x, you just swap the 2 things. So that's a very easy AS code to see. And the plan is to make these multiples of every vector in the matrix B, and then add that one and subtract that one according to the instructions that come from matrix A. And of course you do that coding in the quadratic bit so that your A format is telling you to take the third one and subtract the second one or whatever it is. You do all that at quadratic speed before you get into the multiplication itself. They make them up front. So this is what's used in meataxe 64 for the primes 5 to 193. For the prime 5, the abelian group used is 5 cross 5 cross 5. So you're adding 3 rows by doing 1 add and 1 subtract. So it still gets a grease level of 3 in some sense. Steve has recently implemented high-performance arithmetic using exactly the same structure, A format, B format, C format, etc., using floating point hardware. And of course, the chip designers have spent a lot of time and real estate on their chips, making sure that floating point runs really, 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 really fast. The result is that the best way of operating with all these numbers is to use floating point, where the floating point numbers are all exact integers being held exactly, so that there's no difficulty with any rounding anywhere. The speeds are roughly compatible, so between 67 and 193, he's outperforming the AS methods by a smallish factor, I think it's reasonable to say. But then I've implemented the 512-bit stuff and he hasn't done that yet, so I've left it as it is with AS. I could switch it to floating point, perhaps I should do so. A lot of people ask me about Strassen. I have Strassen is part of meataxe 64. I mean, let's say that before I start, but it's surprisingly useless. So what happens is, you see, you've got a lump of computing. You've got a chip and some memory and some printed circuit boards and some cooling devices and all sorts of stuff like that. You've got to be able to get all this stuff in and get the data out and all the rest of it. It all takes heat, it all makes heat, it all takes space. And what that means is that the data is much faster to get at if it's close to the place where it needs to be. Which is fairly obvious. You can't beat the speed of light anyway. But it's worse than that because it costs real joules to move it about. Strassen saves work, but it requires more data movement. And I can imagine computers of the future having a small amount of rather faster memory, like they used to have 30 years ago, whereby you could no longer afford to use Strassen anywhere, that the result would be that you end up moving more data about, and that costs you more time than you gain by using Strassen. So I wonder whether there might even be a theorem that some model of the real world, Strassen is precisely useless. In any way, case, whenever I say that multiplication is cubic and anyone pipes up and says it isn't, it's 2.67 or 2 point whatever it is, I have yet to see any model of the real world for which that's true. I don't think it is true. I think multiplication is cubic in a three-dimensional world. It might be a little bit faster. I worry that maybe the cauliflower theorem will tell us that you can do a little bit better than that, but I've never really got my head around that. Okay, so that's the meataxe stuff. So now we come on to the rant. So I claim that the whole software world is determinedly ignoring the design of the modern computer. That is what seems to be the case. That you've got multiple cores, you've got multiple levels of cache. This is the elephant in the room that we all ignore. And I'm as guilty of this as anyone else until a few years ago. Let's take our first steps. What do we need to do to program today's computers? Now, I don't expect there to be any or possibly one or two people who actually take this to heart. I know how hard it is to make use of this stuff, and it ain't worth it. But what does it look like? Let's have a look. My earliest mistake, and this was on a transputer in 1991, was to ignore load balancing. What you've got to do is to make it so that your machine doesn't run as fast as its slowest step. It runs as fast as it can, which basically means that if you've got 32 cores, you want most of them at least to be doing work most of the time. It's surprisingly difficult to achieve. And the missing piece, I claim, is a scheduler. Somewhere in any decent system on a modern computer, you have to have a little piece of stuff whereby you can put work into it and get work out of it in such a way that when this guy's done a bit of work, it goes back and gets another bit of work. Now, that doesn't seem like rocket science, does it? But of course, if you're doing an 8-year project, or even matrix group recognition, 8 years is probably too short, you need something that's stable, standard, fast, and functionally rich. Well, I haven't seen one yet. If anyone knows of a solution to that, I'll be amazed, because I've looked quite hard. And there's a lot of them that are stable but not very fast, and standard but not very functionally rich or whatever. But you need all the cookies in the cookie shop before you can build a 10-year project on top of it. And there's nothing there today, as far as I know. Then there's the memory hierarchy. You can't ignore all the multiple levels of cache. So I've given some approximate numbers. These are sort of meaningless in a way, but how long does it take to, throughput terms, to get some 64 bytes of data from L1 cache? About a quarter of a nanosecond. Then you've got your L2 cache and your L3 cache. Gradually getting bigger, gradually getting slower, until you come to your RAM, which is typically huge, but pretty slow. So what we're saying here is that it's perhaps 600 times slower to get data from memory than it is from L1 cache. So anyone who ignores that is in serious danger of writing a program that runs 600 times slower than it would if they sorted it out and did it a little bit at a time. I'm not sure about disk. I've decided to rub those numbers out because SSD is starting to make a difference there. But it's still going to be bigger, it's still going to be slower. The trend is obvious. You need to keep your working set, the little bits of data you're working on, tiny. 16K is typically how much you get per thread on a hyper-threading machine on L1. So you need to be working with 16K at a time, even though you've got however many hundreds of gigabytes available. You've got to do it 16 kilobytes at a time. Right, now this must be the vaguest slide you have ever seen. This is a lesson in computer science. How do you do something? I guess everyone in this room has attacked this problem at some point. What you do is you chop it into a few smaller pieces and then call a routine that does those smaller pieces. That's how you do it. And how do you do those smaller pieces? You chop them into yet smaller pieces and call a routine that does those. Matrix multiplication in meataxe 64 has 11 levels of that. And I don't think I've got enough. I'm worried. There's a couple I've probably missed out. It's not always easy. I mean, matrix multiplication just chops naturally. I mean, you've got to multiply this by this, and you've got to multiply that by that. It just chops up all by itself almost. So I'm attempting an easy problem here. But with the tools that there are for software development these days, it needed to be easy, I can assure you. So here are the 11 levels of chopping in meataxe 64. Might be worth just running through. This is the one I haven't done. So when it doesn't fit in memory, you should really just chop it up into 2 or 3 pieces in both directions on disk, because you've probably got a huge amount of disk. Perhaps I should give you a little fact here. I have yet to find a computer on which I can multiply a matrix of a size that we've optimized that takes more than a day to do so. It runs out of memory. You can't fit a matrix into memory that takes more than a day to multiply. Now, maybe someone's got a ridiculous machine with about 1 core and some number of terabytes of memory where that won't be the case, but I'm not going to use it. So the first thing you do is you do slices of A and C. You're a bit short on memory, so you're just reading a bit of A and you multiply it by B, which you've read in. I don't think there's any way of avoiding that. And that produces a slice of C. And then you go on and do the next slice of A. And then once you've read in a slice of A, you chop it in memory in both directions, actually, so that you can use multiple cores to do the various bits of the multiply. And then within one core now, you do maybe 3 Strassen steps, and that's really only because you've got this vast expanse from 2 megabytes of L3 up to 500 gigabytes or something of real memory. So there is actually space to do a bit of Strassen. And then you do the extension to ground field extractions. If you haven't got an extension field, you don't need to do that. And then you do the format conversions. And then you chop, after you've done the format conversion, chop it up a bit more so that your matrix C fits in L2 cache, which is 256K typically, 128K perhaps. And then you have to chop B so that that fits in L1 cache after it's been greased. So you haven't got many rows. So by this time, the matrices you're working with, basic matrix B, maybe got 32 rows and 1024 columns or something. But your 32 rows are actually 8 grease blocks. So for each L1 cache, you've got to do 8 things of greasing up 4 rows to make 16 rows. And then you multiply your grease blocks, your multiple grease blocks. Anyway, eventually you get down to the stage where you're doing some real work. Well, that's actually a long way down, right? I mean, you might think that multiplying matrices is all to do with work. That ain't the case. You spent 90% of your work, of your programming work, is chopping it up and calling subroutines to do the next bit down. There comes a time when you actually have to do some work, and you want to do some work as fast as you can, but that's not the main problem. Another problem is a synchronization issue. So this is, again, general programming. There's another vague slide. Lots of things. You want to do something, and then you want to do something with what comes out of that. But you don't want to use the output until you finish making it. That is a surprisingly difficult problem as well. It's a really bad mistake to use data you haven't finished making. I hope you can all see that. And finished making is nowhere near as simple a thing as you might think. I mean, with a clock speed of 2.5 gigahertz, light travels that far. So you might have made it over here, but this guy doesn't know anything about it yet. This is pure Einstein, and it ain't as good as that. I mean, we need a solution for these dependency problems to make it so that you don't have to worry as a programmer about trying to make it so you don't use data until you finish making it. We want a stable, standard, fast, functionally rich solution to that as well. No doubt it will eventually emerge. So you can start to see why it has taken me 8 years of my life to try and get meataxe 64 to do what it does today. Now I write my bottom levels in assembler. The modern computer has all sorts of wonderful instructions. It's got conditional moves, it's got vector registers and things that tell you where the top bit of an integer is, and all sorts of wonderful instructions that have been added over the last decade or two. It's very difficult to persuade the compiler to use these things. Now, Steve again would say that with great expertise and work, you can be assembler aware and write your C program or C++ program knowing what you want to come out, and therefore you keep fiddling with your input until you get what you want. I have a different approach. I know what I want, I just write it. But I don't know if you've looked at assemblers recently. I guess probably there's about 2 people in this audience who have. The assemblers have not noticeably changed in 40 years. They are exactly the same as they were before. Except it's now, instead of having 20 instructions, you've got 1,000 instructions. I can never remember how to spell them. I have to look up every one. Surely we can do better than this. Now, this is the catch-22. Nobody in their right mind writes an assembler. Okay, I do. Nobody produces a better assembler because nobody would use it if they did. Surely we've learnt something in the last 40 years that could usefully go into an assembler. It hasn't happened. It really hasn't happened. I just cannot understand why it hasn't happened. Well, maybe I've actually told you why it hasn't happened. But anyway, so here are my general conclusions. The computer industry has been slow to react to the changes of hardware, and that software development is now way behind the hardware. The computers you imagine you are programming do not resemble the computers you are actually programming most of the time. You write a program and it starts at the beginning and proceeds to the end by way of the middle. It doesn't use cache, it doesn't use, well, it might use cache if you're lucky. Typically uses one core. You're obviously losing a factor of 500 or something on performance. There are early signs that this is changing. I'm hoping it will change. I'm hoping I'll live long enough to see those changes, but I suspect I'm going to need to be over 100 before I really see them properly. So let's turn to the results now. What does meataxe 64 actually achieve? This was a heroic project. I mean, this was Linton, Niebuhr, Niemeyer, John Thackeray and myself, joint work for over a year to get Gaussian elimination to work on my stupid thread farm. But the result is that a full Gaussian with transformation matrix is now about the same speed as matrix multiplication. So if you want to do a Gaussian elimination in 1,000,000 dimensions over a relatively small field, you can probably do it. Oh yeah, I should have mentioned you as well, yeah. There are about 10 people involved in trying to sort this mess out. But it does work. So how fast is it? The biggest practical use I've made of this, I mean, nobody uses my stuff unless they have to. So where's David Craven? He's hiding there somewhere. There he is. He said, I want you to chop up this 400 and whatever it is, 440,000 dimensional module over GF25 to get a module for 3F22 in about 110 dimensions, or no, about 11,000 dimensions, I think it was, I forget. So I used the Lovelace machine in St Andrews. I had a bit of trouble with it because I haven't got a characteristic polynomial, so I couldn't use Holt-Rees. So if I wanted to find an element with nullity non-zero, I had to look at all the other modules that might be in there and try and guess, work out in rather fewer dimensions than 440,000 a nice element to compute the null space of. I did try. I mean, my first attempt, and I said it'd take 3 days. I spent the first day prattling around with 440,000 dimensional matrices trying to find something that had nullity. And I thought, this is stupid. So I logged off and prattled around a bit on my laptop to find out what I should actually be doing, and went back and did it. That only actually took 2 days. Monster multiplications take about a couple of minutes on these big machines these days. I mean, I remember in Arkham, Thackeray and I, wherever he is, multiplied 2 monster matrices on about 5 computers in about 3 days at the 1998 Nikolaus. It's about 2 minutes on a typical machine now. Not quite 0, nichts, but it's getting there. I don't have any ambitions to try and make it any faster. I don't know how to do that. In fact, we did actually have a go at making it faster and spent a week or two, and it speeded it up by about 8%. So I deleted that. I thought 8%, even my outrageous obsession with performance was not enough. 1,000 lines of code to gain 8% mod 2 only. I thought, nah, I deleted it. So the takeaway, simple thing, is that if you want to do work with a million by million matrix, and all you want to do is Gaussian elimination or multiplication, you can probably do it. Bigger than that, you might have to scratch your heads and put rather a lot of computer power on the cloud or something, but you can do it. That is the scale at which meataxe 64 currently reaches. It only does simple jobs. It does multiplication, Gaussian elimination. That's all it does. So I'd like to do characteristic polynomial. I think I know how to do that. We spent hours and days trying to discuss how to do that in a cache-friendly, multi-core, blah, 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 blah way. But there are still issues, so it hasn't been done yet. And of course, if you do your characteristic polynomial, you're probably going to have to factorize it before you get too much older, or at least find the roots. And I don't have to do that either. That gets quite messy. You can probably find the roots if your field is of order less than 10,000 or something, but after that it's starting to get a bit gruesome. Just try every possible route and see if it works. No, that can't be the way to do it. I still don't know how to find the order of a matrix. Now, I don't know, Charles, if you can tell me how to find the p part of the order of a matrix. I don't know how to do that. It doesn't seem to be that obvious. No, talk about it afterwards. Of course, you've got to be able to factorise p to the d minus 1 or q to the d minus 1. That would need an oracle. I can't avoid that. But even getting the p part seems quite hard to me. And this is, I've quoted this before, I think first time about 30 years ago. If it's not cubic complexity, it's not an algorithm at all. So it's got to be cubic complexity, right?
Well,
there's some stuff to do.
It was your pointing out that it has to be cubic complexity drove us to get the order algorithm to be approximately cubic complexity.
Yeah, but now I want to do million by million matrices in a day.
Well,
so it's not just cubic complexity, it's got to be good.
Yes. Well, no.
Another thing I find trouble with, and I guess the matrix group recognition seems to have this problem in spades, is that you want to be able to write something that does something really good, and then you want to build something on top of that that uses it, and then you want to build something on top of that that uses that, and so on. And we haven't got any way of doing that. I mean, that 11-layer model for the matrix multiplication, every one of those was ground out by hand. That's got to be bonkers. If we're going to have 20 or 25 layers of stuff so that you can just feed in a couple of matrices and have it tell you what the group is, you need to be able to put these layers together better than that. And we haven't got a way of doing that either. Got some ideas, but no code. So here's my overgeneralization. Simple algorithms can be speeded up by a huge factor. 500, 100, something like that. But you need to spend 50 times as long writing them. Is it worth it? Probably not. In the meantime, anyone who wants to use meataxe 64, you've had your government health warning. The ease of use is not a high priority. But Steve's actually trying to put it into GAP. I think he's put some bits of it into GAP already. So the idea is that this should eventually be available to GAP users to operate at this sort of pace. That is not just a pipe dream, that is work in progress, I'd say, but you need to ask Steve about that. Just beware, it might take 50 times as long as you thought to write the programs to use it. It's all very well me producing wonderful systems, but if you don't use them properly, you'll mess it all up. And although there are limits to how much you'll be able to mess it up, my experience with users, limited though it is, suggests that it is still vast. I'm done.
Some calculations I've done, and I think also some number theorists have covered this,
Fine, yeah. Yeah, it's implemented properly. Actually, it only goes, it does quadratic extensions, cubic extensions, and all fields up to 65536. Oh, no, oh, no. Yes, I have tried to do that. I tried to do some of that in about 1988. And I don't actually know what split means. I mean, it's just, yeah. I'm not going to touch, I'm not going anywhere near it. No. Yeah. Yeah, we need to calculate the determinant of a matrix mod 8 according to Gabby, and we don't know how to do that. I'll take that one offline. I have a thesis on the subject.
I've only done one serious calculation using in parallel, but particularly from what you're saying, the obvious thing for most exercises I would have thought would be not to take, say, a matrix multiplication and split it up so you're doing it in parallel, but rather, because you probably want to do more than one matrix multiplication, do the different matrix multiplications and these different things. I mean, that superficially seems to get round all these problems we're talking about. I mean, that's the way we did it. Not that we were multiplying matrices, but I mean...
Well, if you can manage to want to do 64 of them at once, then you can at least use 64 cores. In practice, you'll find that one of them takes 5 times as long as the other 63, and load balancing is an absolute nightmare. You've just got to balance the load. You've got to be able to give the next processor a little bit of work to do as soon as it finishes the last one. Believe me,
Yeah, okay.
that's not the way to go.
It worked, but it added about 30% to the programming time.
Yeah, and it probably speeded it up by a factor of 3. I want a factor of 100.
Well, we did,
Yeah?
Well, there was an expensive machine, of course, right?
Yeah, okay, well.
But another thing, there's a lovely little algorithm in the hacker's delight for counting the number of bits that are set in a word. Is that any use to you? Do you use that?
There's a machine instruction, which you won't be able to get at in the compiler, that does it all for you in one instruction on half a clock cycle.
Yep, okay.
No, you don't need any clever algorithms for that. You just need to write an assembler.
Yep, okay. I'll bear that in mind, but bloody well, I'm not going to do it.
Yeah, we're in early days in this experiment. How do you program today's computers? We haven't really got much of a clue. And where's Madeline? How does she put it? I don't know what I'm doing.